Hello and welcome. Today, we will present a method for mining frequent infix patterns from concurrency-aware process execution variants. This paper is published in the conference proceedings of the Conference on Very Large Databases 2023 in Vancouver. The authors are Michael Martini, Daniel Schuster, and Professor Will van der Aalst from RWTH Aachen University and the Fraunhofer Institute for Applied Computer Science. Process mining is a data-driven approach to analyze and improve processes by extracting insights and knowledge from event logs generated by various IT systems. Data in the form of events in process mining is stored in event logs. A common way to work with events of event logs is to group them together into cases. A case then represents the execution of the activities in a process to fulfill a specific goal. As an example, consider the production process in a wheelbarrow factory. A typical case in the factory could cover handling a production order from opening to the final delivery of a wheelbarrow. A case can run as shown in the example. The production order is opened, and then the material is requested. We then produce the wheel, the frame, as well as the skip and paint it. Last, we assemble the wheelbarrow and deliver it to the customer. This unique sequence of events is then called a variant of a process. Multiple cases can follow the same variant. As such, variants represent a good way to group similar behavior observed in a process and represent a larger number of cases. For example, two other process variants are shown below, which vary compared to the first variant in the order the frame, the wheel, and the skip are produced. The variants as presented here, however, have a glaring weakness: they order events as they occur in a strictly ordered sequence. Event A happens before event B, and so forth. However, in reality, workloads, such as producing the component parts of the wheelbarrow, are often handled concurrently, and the strictly sequential ordering we impose is only an artifact of the storage of event data in event logs. To address the limitation of variants, concurrency-aware variants or short concurrency variants are used. Concurrency variants allow for modeling both sequential and concurrent relations of activities performed in a case. To continue our previous example, the previous three variants, which showed different ordering on the production of the wheel, the frame, and the skip, can then be represented by a single concurrency-aware variant. As such, concurrency variants are a powerful tool to group the cases of a process and analyze them. Concurrency variants, by their ability to group behavior observed in a process, serve multitudes of usages. They allow for visualizing the flow of events in a process and thus present an essential first step to gaining insights into a process. Furthermore, they can be used for process discovery, which aims to discover a process model from event data. By their ability to group behavior, the discovery algorithm only needs to consider the unique variants instead of the whole event log. Lastly, they can be used to speed up conformance checking. Conformance checking compares a to-be process model with the historical event data stored in an event log to find deviations in the event log and divergence from the planned execution of a process. Concurrency variants, by representing the unique variations of a process, again allow us to summarize the underlying event data and speed up the computation. Through their wide range of applications, variants are essential in process mining. Unfortunately, they also present challenges. Process variation often follows a power law distribution or, more closely, a Pareto distribution. As such, few variants represent the majority of cases of a process. Most variants in a process thus only occur a few times or only in a single case. As such, variants can still be tedious to work with and hard to find commonality in. To address this issue, we present in the paper a novel approach to mining frequent shared behavior of concurrency variants that allows us to find structure shared even across variants with only a single associated case. To mine shared patterns of concurrency variants, we present a novel algorithm. The shared patterns we call infixes can be mined from concurrency variants by first observing that concurrency variants can be modeled as labeled, rooted, and ordered trees. We call these trees variant trees. We show such a variant tree and its associated concurrency variant below. Infix patterns of concurrency variants can be modeled by a new kind of subtree of variant trees called an infix subtree. Infix subtrees preserve the sequential ordering of activities by ensuring that activities in an infix occur in a closed sequence. We then present a frequent subtree mining algorithm called Valid Tree Miner that mines frequent infix subtrees from variant trees. We compare the proposed Valid Tree Miner against a state-of-the-art frequent subtree mining algorithm and observe gains in runtime and memory usage. Furthermore, we observe exponential growth in the number of frequent infix subtrees for a decreasing frequency threshold. The Valid Tree Miner is integrated into the open-source process mining tool Cortado. In Cortado, the Valid Tree Miner algorithm can be used to mine frequent infixes for visual analysis of event logs and process model discovery. We would like to thank you for your attention and invite you to read the full paper under the provided QR code on vldb.org. If you have questions, feel free to contact us via the provided email addresses.